Yeah. So now I'll discuss the spinor representations. So let us start with the spinor representations, which is, for example, like two-dimensional representation of SO3. The link between the two are basically through this 2 by 2 Pauli spin matrices that satisfy this sigma A sigma B equal to delta AB plus I epsilon ABC sigma C, and AB runs from 1 to 3, and epsilon ABC is the structure constant for SU2D algebra, which is the fully antisymmetric Lebesgue tensor. And this form from where we can construct the SO3 algebra, and also the anti-commutator from algebra. We have the sigma sigma the anti-commutator equal to twice delta AB, and the product of two Pauli spin matrices is the proportional to the third one, that is sigma 3 equal to minus I sigma 1 sigma 2 and so on. So altogether, we can define the generators as x12 equal to minus I by 2 sigma 1 sigma 2, x23 equal to minus I by 2 sigma 3, and x31 equal to minus I by 2 sigma 3 sigma 1. And this is just if you try to mimic the geometrical notion that we have discussed earlier, and that this follows from that one only. Now, to derive the commutative relations, it suffices to know that the Pauli spin matrices satisfy the Clifford algebra, and that would be sufficient information for us to construct the Lie algebra. Now, we can express the SON generators as bilinear products of Clifford elements. Then we can build the representations of orthogonal algebras, which is equivalent to construction of all possible Clifford algebras and the space on which they will act. Now let's try to recall the harmonic oscillator. So in the harmonic oscillator operators, we have noted how they act on this thing, like for example in the angular momentum algebra, right? So they generate a finite dimensional Hilbert space spanned by the states of the form, for example, like bi1 dagger, bi2 dagger, and so on, bik dagger, acting on this omega, where omega is the basically the active. We can think of a people function here. And then you get this state where these are basically fully antisymmetric indices. Okay, and this can be thought of as an a complex totally antisymmetric tensor which form the representation of the SUN. Now we define the quadratic operators as Tj, which is b dagger bi minus 1 by n delta bk dagger bk, which form an SU2 Lie algebra. So this part you can think just like a trace part, and this is separating that trace part. So from and this t equal to 1 by twice n bk dagger minus bk dagger bk, which is basically just a number and operator kind of thing, and that from the E1 Lie algebra. And here Tj Ti Tlk commuter is given as delta Li Tk minus delta Jk Til, and if you define this T, which is the E1 generator that will commute this TLK generator or the SU2 or SUN generators here. So you have get a subspace which are basically orthogonal to each other, SUN and E1 part. Now, except for the vacuum state and the totally antisymmetric tensor with m indices, the states of the Hilbert space are thus the fundamental representations of SUN. So one for each node in the Dynkin diagram. So that will be clear when we talk about some kind of example. So let's consider the remaining quadratic combinations, like for example Aij as Bibj or Aij covariant as Bi dagger Bj dagger, and these transform as antisymmetric two forms of SUN. Okay? So then Tji AKL is basically your delta J AIK minus delta JKIL and their conjugates and so on. So you can construct the higher representations and the combinations. So more comparisons show that they close on SUN cross E1 generators. So you can certainly find out this Aij AKL commuter in this following form. And the quadratic operators generate the larger SU2n Lie algebra with the embedding. SO2n encompasses contain basically SUN cross E1, and that's why you can define the decomposition as 2n of representation of SO2n as n plus n bar under this SUN, and the E1 charges are such that because they are conjugates, they are automatically conserved. And the adjoint representations can be given as 2n into 2n minus 1 by 2 of SO2n. And in terms of the SUN representations, you can decompose like 1 plus n square minus 1 plus n into n minus 1 by 2 plus n into n minus 1 by 2 conjugate. So they are basically real representations. Now let's try to focus on the SO2 spinners. So all states of the Hilbert space have an E1 charge, and so vacuums into the vacuum state also, like where the T omega acting on this unit charge, so it's like omega. And antisymmetric state made up of n oscillators given like this particular form, and so then the T eigenvalue is given as 1 plus n. You can build representation of SO2n by repeated applications of the double raising operators Aij on the vacuum state, which generates all state with even number of oscillators. Right? So a similar action starting on the oscillator state generates a second representation made up states with an odd number of oscillators, and these are two spinor representations of the SO2n. Now let's try to figure the example. Let's try to build up the spinor representation of SO6. So we start with a SO3 Dynkin diagram to which we append the vacuum state and the totally antisymmetric state, which are the open dots. We construct the two spinners by hopscotching across the Dynkin starting with the vacuum state. So this is the SO3, and then you have the vacuum state, and then you have the hopscotching and this thing. And you have a one oscillator state, and then you can also, there's another way of hopscotching like this. So using that two spinor representation in terms of SO3. And then what, for this you get 1 plus 3 bar, right? So you have a 1, and then you have a this 3 points are connected, so it's like a 3 bar. And then here these 3 are connected, so 3 plus this is left out, so this is 1. In this way you can construct these representations. Then they are evidently complex representations and conjugate to each other. So for SU4, these are basically 4 and 4 bar of SU4, and SU4 is basically homomorphic to SO6 representations. Now for SO8, so we start with like SU4 in a Dynkin diagram, which is like this, and then we have this vacuum state. The first hopscotching gives you like this and this. So it's a real spinor representation of 8 components, which contain SU4 represents in the following form, like 1 plus 6 plus 1. So this is like a 1, so 1 plus 6 plus 1, right? And then the second hopscotching gives you like, when they are not connected, so like a 4 plus 4 bar. So this is the way of constructing the second spinor representation made up of, which is also 8-dimensional real representation of SO8. So in SO8 representation, you can write it down in terms of a 1 plus 6 plus 1, or also you can write down 4 plus 4 bar. So now, interestingly, it is important to note that the structures of the spinor representation of SO2n differ based on the whether the n is even or odd. So that means SO2n you considering where n is even or odd, that actually differs the characteristic of the representation. For example, when n is even, the two spinor representations are complex and conjugate to each other. Okay, like for SO8 when you consider it. But when n is odd, the two spinners are real and differ from one another. That we have seen earlier. In either case, both have the same dimensions. The two spinor representations of SO2n correspond to the rabbit ears of its Dynkin diagram. So in this particular Dynkin diagram, you can, let's see the rabbit ear part of the series giving the two spinor representations of SO2n. Now for orthogonal algebras in even dimensions, and the first n-2 fundamental representations are antisymmetric tensors, and the last two are spinor representations. Basically, right? So then you can consider, like for Dynkin diagram, Dynkin levels 1, 0, 0, there's a tensor of this structure Ta, and the dimensions 2 and 1, C1, and then so on. If you go the last two 0, when the elements are 1, 0, and 0, 1, they are basically chi and chi prime. They 2 to the power minus 1, 2 to the power minus 1. This is the spinor representations, and others are basically antisymmetric representations. Now, when n is even, the chi is conjugate to chi prime, and when n is odd, is chi and chi prime are real, and they are inequivalent representations. Now, for the SO2n plus 1, we start with the expression of SO2n generators in terms of the n harmonic oscillations. Then we add one more B and B diagram. Okay, so this would enable us to construct the generators of SO2n plus 2, but we are interested in SO2n plus 1 subgroup. So in the embedding SO2n plus 1, which contains SO2n, and then this 2n plus 1 dimensional representations can be written in terms of SO2n represents as 2n plus 1. So the coset SO2n plus 1 coset SO2n is just the 2n representations of SO2n. So in terms of SUN, it decomposes as n plus n bar. The extra harmonic oscillator allows us to write down several quadratic expressions with respect to the correct SUN transformations. The commutator of the combinations, for example, like AI, you can define as in the n representations as BI plus B dagger, and for n bar, you have a BI dagger is you can write down the additional part B dagger plus B. And interestingly, they closes on the SO2n cross E1 algebra. So that AI AJ commutator, if you write down, you get 2 TJI plus 1 by n delta IJT. This is the trace part. And they are the coset generators of SO2n plus 1 coset SO2n. By adding one oscillator, we have doubled the size of the Hilbert space, right? That can be spent by like this, and then another copy will be like B dagger times this. So each branch transformed by itself under the action of the SO2n generators. But AI and AI covariant and AI countervariant are the basically coset generators that make transitions between these, crisscross kind of thing, between this either this to this and this to that. Vice versa, it can be done by these coset generators. For example, AI omega will give you the BI dagger, B dagger, omega, and AJ like minus BJ dagger, BI dagger, omega in this way. So this produces a crisscross pattern of states. It is manifestly self-conjugate and it's half of the states in the Hilbert space. The fundamental representations of SO2n plus 1 differ from those of SO2n by having only one real spinor representations. For example, if we think about SO9, we start with two copies of SU4 Dynkin diagrams augmented by two singlets. Like these are two SU4 Dynkin diagrams, and there's the singlet state. Now, because in this is an odd dimension, so you start from here, and then you can see the crisscross pattern here, and that's why the leftmost represents the vacuum state, and the diagonal dots represents the action of the AI. I mean, this one. Right. So now they link the states of the real spinor representations. Thus, the 16-dimensional SO9 spinor representation in terms of the SU4 subgroup is written as 1 plus 4 plus 6 plus 4 bar plus 1. And that is evident from here 1 plus 4 plus 6 plus 4 bar plus 1. So in this crisscross pattern, they can define. But this also shows that there is only one real fundamental spinor representation in the odd numbers of dimensions. But in the even dimensions, the two spinors can be either real inequivalent or else complex conjugate to one another. And similar to SO2n, also for SO2n plus 1, we can write down their Dynkin levels, okay, and then their tensorial structures and corresponding dimensional representations. And here you can see that the last one is basically the spinor representations, and this is just a double of the SO2n1, and this is the 0, 0, 0, the last element is 1, and the dimension is 2 to the power, and this is the real representations.